Hello, everybody, and welcome back to Unit 1 of Regents Chemistry, Math of Chem, where we will be talking about accuracy and precision today. So, normally, when we perform an experiment in the lab, we try to do three different trials or three different times repetitions of the same experiment. We call them trial 1, trial 2, trial 3. And the reason why we are doing that is because we want to know how precise our measurements are, which means how close our measurements are to each other. If they're very close to each other, that means we are doing the experiment in the exact same way every time. But if, let's say, our measurements are very different from each other, then that means we are doing something different each time we are performing this experiment. So that's the first thing that we want to check whenever we are doing an experiment. That's why we do three trials. After we have checked the precision, then we go ahead and take an average of whatever our results are from those three trials, and that gives us our average result, which we call our experimental value. What we do with this experimental value is we compare this with our with an accepted value, which we can get from literature or from experiments that other people have done, or from, like, in our case, when we do some experiments in the lab, we basically just compare them from, like, the literature values, like proven actual values, which we know that this is the exact amount. And the reason why we do that is because we want to know how accurate our measurements are, which means how close we are to the actual value. If we are very close to the actual value, then that means we did the experiment right. If we are super far away from it, then that means we have to do the experiment again correctly. So the way we figured that out is we use these two numbers to find the percent error, and the equation for that is given to you guys in table T. It looks like this. So basically, it's just you take your experimental or measured value, subtract accepted value divided by the accepted value again, and then times 100. So this gives us the percent error. Remember, if you get a very small percent error, that means we are very close to the actual value. If we get a very large percent error, then that means we are very, very far away from the actual value, and we might want to consider doing the experiment again. So these two things, the accuracy and precision, they give us the uncertainty in our measurement, which means we cannot say with 100% surety that our experiment was correct and we got the correct values, or this is what the exact correct values should look like. So just a quick review: precision is how reproducible is the result, which means if we perform the same experiment multiple times, how likely are we to get the same result? That's what we mean by precision. And then accuracy is how correct is the result, which means when we compare that to a trusted research or something, how close are we to their answer? So let's quickly look at some of the examples of precision. So here we see this picture. As you guys can see, all of these arrows are very close to each other, but they are not close to the target. The target should be in the middle. So when they are close to each other, that means they are very precise. They have a high precision, but because they are not close to the actual value, they have very low accuracy. Next up, we have this picture where the arrows are very, very far away from each other, so they have very low precision, not close to each other at all, but they are kind of close to the center, so we can say that they have low precision, but they have highish accuracy. Next up, we see all of these arrows scattered around everywhere, so they are not close to each other, which means they have low precision, and they're also not close to the target, which means they also have low accuracy. Finally, we have this picture. All of these arrows are very close to each other, so they have a very high precision, and they're also very close to their target, so they have very high accuracy as well. So accuracy, as we said, is basically how close our value is to, like, an actual value. So we refer to an accepted value from, like, a trusted source, a reliable reference, something like that, and then we compare our experimental value, which we collected in the lab, with that accepted value. So sometimes you might only be asked to find the error and not the percent error. So the difference between finding an error and a percent error is that for the error that's just the difference between your experimental value and the accepted value. So all you have to do for this one is experimental value minus accepted value. That's it. Okay, that's all you need to do to find the error. However, what you guys see most of the times in Regents, for the most part, is the percent error and not just the error itself. So percent error is where we use, it has to be in percentage, and that's where we use this equation that is given in table T in your reference table packet. And remember, table T is on the last page, page 12 of your packet. So let's quickly look at how can we use that equation to solve some of the percent error questions. So here the question is saying you measure the freezing point of a liquid to be 1 degree Celsius when theoretically the liquid freezes at 2 degrees Celsius. So what is the percent error? Now, things that we know here is that our experimental value is 1 degree Celsius and the actual value is supposed to be 2 degrees Celsius. So we can go ahead and put this in the equation. So we do the measured value, which is 1 degrees minus 2 degrees, the accepted values divided by 2 degrees Celsius times 100. Okay, we do our math and we get negative 1 over 2 times 100. Now, the thing to remember here is that we can never ever have our percentage in as a negative number. So we'll just ignore this negative part and we'll just consider this as a positive number. We'll just go with 1 over 2 times 100. And that gives us a percent error of 50%. Now, as I mentioned earlier, 50% is a very large error. So this is just telling us that we definitely do want to do this experiment again because our value is not correct at all. So another example, we have a student that determines the electronegativity of element fluorine, which is 3.6. What is the percent error? The actual electronegativity of fluorine is 4.0. Do not let the word electronegativity bother you right now because we have not discussed this yet, but we will get to this eventually. So for now, just take this as a fancy word. So the experimental value here is 3.6. The actual value is 4.0. We can go ahead and put these numbers in our equation. So the measured value, we do 3.6 minus 4.0 divided by 4.0 times 100. Okay, when we do the math, we get negative 0.4 divided by 4.0 times 100. Once again, we cannot have our percent error as a negative number, so we'll go ahead and just ignore that negative part and continue with the rest, and that gives us a percent error of 10%. And 10% is a kind of okay error, but we would want to have an error less than that. 5% is typically considered like a reasonable range. 10% is still a lot. We might want to do this experiment again as well. Alrighty. So that was it for this part of the unit. Happy learning, and I will see you guys in the next one.